Hi guys, in today's video we're going to be taking a look at the relationship between the total mechanical energy and the work. So total mechanical energy is just potential plus kinetic. And then in the case today we will have a non-conservative force acting, so we'll look at how to deal with that. So the first thing we need to do is remember what it means to be conservative or non-conservative. So a conservative force is defined as one in which the work done does not depend on the path taken. Whereas for a non-conservative force, the work that a non-conservative force does will depend entirely on the path that you have taken. So an example of a conservative force is just going to be the force of gravity near the Earth's surface. And so the main takeaway here is that for a conservative force, we can define some potential energy, which in the case of gravity is just equal to mgh. And so we see this potential energy is defined at every point in space. And that's because the work done does not depend on the path it took for you to get to this point in space. So we just need to know the height and we can define the potential energy. But for a non-conservative force, in general, we cannot define any kind of potential energy term. So these are only defined for conservative forces. So if we have something like friction, which is a non-conservative force, there is no potential for friction. So whenever you only have conservative forces acting, you have what's called the conservation of mechanical energy, which just means that the initial mechanical energy, which is kinetic plus potential, will be equal to your final mechanical energy. So it's not going to change. It might change forms between kinetic and potential, but the total value will not change. But if you have non-conservative forces acting like we do today, you're going to have to generalize this equation. If we have a non-conservative force, the total mechanical energy is not conserved. But we can deal with that in the following scenario. We can say that we have some initial total mechanical energy. And then to account for the change that the non-conservative force does on this total mechanical energy, we will just add the work done by this non-conservative force. So WF is the work by the non-conservative force. And that's just going to tell us the change of mechanical energy. So that will get us straight to the final mechanical energy. So this right here is just going to be our general scenario when we don't have only conservative forces. When there's a non-conservative force acting, this will be our general equation. Our mechanical energy plus the change in that mechanical is going to be equal to the final. So let's look at the problem statement for today, and that reads as follows. A truck with mass M has a brake failure while going down an icy mountain road of constant downward slope angle alpha. Initially, the truck is moving downhill at a speed of v0. After careening downhill a distance L with negligible friction, the truck driver steers the runway vehicle onto a runaway truck ramp of constant upward slope beta. The truck ramp has a soft sand surface for which the coefficient of rolling friction is μr. What is the distance that the truck moves up the ramp before coming to a halt? Use energy methods. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here. So I've just labeled the final height and the initial height. So the truck travels from some initial height. It will travel down ramp 1, up ramp 2. And so on ramp 2 we have some friction. And so it's going to come to a stop at some final height, which is some distance d along the ramp. And so the problem asks us to solve for this distance d that is along our second ramp. And so our first step here, what I always like to do first is to think about how energy is going to change during this system. So we have a non-conservative force, so our mechanical energy is not in general conserved. So what I want to write down first is just keep in mind that our initial mechanical energy should be greater than final. And that's just to say that it starts with some energy, and then the friction force here along this second ramp is going to work to take away some of that energy. So if you just think of a block sliding along a surface with friction, that friction is going to work to take away its kinetic energy, and eventually it'll reach rest where it has zero energy. So it's the same idea here. This friction along the ramp here will work to take away some energy from the system. So this is going to be good to check. Once we sort of set up our relationship and we get the final result, we want to make sure that our energy initial is going to be greater than our energy final. And so we're going to have plus and minus signs to worry about along the way, so this is going to be a good check at the end. So our real idea today is that we want to look at our kinetic energy initial plus potential energy initial. So this is our total mechanical energy. And so we know this is not conserved, but if we take into account the work done by our non-conservative force, which is our friction force, then we see we should be able to get back to our kinetic energy final and our potential final. So this is our form from before, from the beginning of this video. And this is going to be at play today because we have our non-conservative force. So basically all we really need to do is solve for initial total mechanical energy, final mechanical energy, and then also this work done. So to start, I'm just going to look at this work term, and then we'll sort of work through the energy terms after that. So for our work term, we know that in general, the work done by a frictional force should just be equal to that frictional force dotted with our displacement vector. So we've done this a couple times before, but remember, for frictional force dotted displacement, the frictional force is always going to oppose the motion. So this will be a negative work done, and it's going to amount to a negative work, which is the force of friction times the distance that the friction is applied over. So in this case, the friction is only applied over this distance d on the second ramp. So our work done by friction is going to be negative force times distance. So now all we really need to do is then note the form of the frictional force. And so in this case, the form of the frictional force should just be mu r times force normal. So we need to remember that this object is acting on a ramp. So this normal force is not just going to be mg. So I'll let you guys pause the video at this moment and try to figure out what this normal force is. We've done this before, and it's outlined in the solution, so you should try to figure this out right now, figure out the total frictional force, and then whenever you have that figured out, go ahead and replay the video. So I'll assume that you've done that, and then we have this frictional force here is just going to break down to mu r times m times g times cosine of beta. And so this is our frictional force, so we can plug this in. And so basically we've just solved for our work. If we plug enough things in, we can get our work term. So now let's just look at our mechanical energy term. So for our initial mechanical energy, we see we have some kinetic energy, which is equal to 1/2 mv naught squared. It has some initial velocity here. And then we have some initial gravitational potential. It starts at some distance above the ground. So we'll set the ground to be 0. And then this would just be mgh initial. And we just solve for the work down here, through if we can sort of propagate that through. So if we plug in this, we will get a negative force of friction, which is mu r mg cosine of beta. And then that's also times the distance. Don't forget to multiply all of this by the distance. So this is going to be the left-hand side of our equation. That's the mechanical energy plus the work. And so then this all should be equal to the final mechanical energy. And that is going to be that the kinetic energy final is 0, because we're told it comes to a halt at the top. So this is just 0. And then the total potential energy is the gravitational potential at this final height, which will just be mgh final. So this here is our relationship. And luckily for us, we see that we're really almost done. All that we don't know is the h initial and h final. But everything else here is something that we know, and then the distance d is what we want to solve for. So really, our only remaining step is to find h initial and h final. And if we look back at our diagram, that just amounts to a little bit of trigonometry. We have these triangles here, right? So we have this beta triangle. We have this alpha triangle. And each of those is going to relate our initial and our final heights to things like length and the distance d. So we should be able to do some trig, and you can follow along the solutions, but you'll get that h initial is going to be L sine alpha. Similarly, h final should be d sine beta. So these are going to be our heights, and if we just plug this into this relationship up here, we can solve directly for our distance d, and then there'll be some amount of algebra, but you should be able to get that your final distance should be equal to v naught squared over 2g plus L sine alpha, and then all of this is going to be over g sine beta plus mu r cosine of beta. And so this is our final results, and all of these quantities over here are known. They would be assumed to be given to us if we wanted to deal with numbers. And so in this case, this is our final answer. Okay, so now that we have our answer, it's also helpful to go back and check to make sure that this makes sense. So if we remember back to the beginning, we said that the initial energy has to be greater than the final energy. So if we look over here back to our relation that we wrote down, we want to make sure that that's the case. And so we see that this minus sign is going to allow that to be true, which is to say we'll start with some total initial energy. We should be subtracting off from that total energy in order to get to our smaller final energy. So we see from this relation here, the initial energy subtracted by some amount will get us to our final energy. Therefore, our initial energy is greater than final energy. So this all checks out and we're all set. So let's go ahead and review what we've just done. We first noted that we expect the initial energy to be larger than the final energy because friction should take away mechanical energy from the system. Then we wrote down a relationship between potential energy, kinetic energy, and work. The work done by friction was calculated by plugging into this relation along with the initial and final mechanical energies. Then we solved that equation directly and found the distance traveled up the second ramp. Okay, so I hope this video was helpful to you, and I hope it sort of gave you an idea of how to deal with non-conservative forces in these energy problems. So if you have any comments on this video or any of the videos here, please leave those on the comments link on TED, which should be to the right of the video link. Thanks for watching.